Hello everyone and welcome back. Today we're going to talk about universal gravitational potential energy. Now I saved this one for last because it's treated a little differently than the other types of energy we have dealt with. I'm going to skip the mathematical derivation and instead concentrate on the conceptual idea behind this relationship and how to use it properly. So first we're going to start with a comparison to the gravitational potential energy we are already familiar with. So here I have change in gravitational potential energy equals mg change in height. So if I took this box and lifted it up into the air, the box Earth system would gain gravitational potential energy. And this is a linear relationship between gravitational potential energy and delta Y. But there's an assumption made here, and that assumption is that Earth's gravitational field near the surface of the Earth does not change. In other words, if I take this box and lift it up 2 meters or 20 meters, within that distance, this value of Earth's gravitational field does not change at all, or at least not enough for it to matter in any significant way. So, what if instead I took that box and lifted it really far away from the Earth? Well, in that case, from my initial point to my final point, Earth's gravitational field gets smaller. Therefore, this equation would not work anymore because g would literally be changing value the farther away I got from the Earth. That is basically why the universal gravitational formula exists at all. So the first conceptual reason as to why we're dealing with this today is because the gravitational field strength changes over great distances. So again, lifting it 2 meters, the field isn't going to change barely at all. However, lifting it 2,000 meters, and there's going to be a change in the gravitational field. That, therefore, makes the gravitational potential energy equation we have already been working with useless for this particular case. Now, since we're talking about great distances and masses like the Earth and other planets, this concept has a very close relationship to something we have already dealt with, which is the universal gravitational formula. If you need a refresher, be sure to go back and check out my video on this topic. Now, alongside this, I'm going to put a graph that represents the force gravitational versus radius, which is the distance between the center of mass between two objects, like the planet and, say, my box. Or this would be the radius. So as radius gets larger, force gravitational gets smaller, but it is an inversely squared relationship. So this force gets weaker very quickly. And if you get really far away, this value is almost zero. In fact, it is close enough to zero that it might as well be for any real purposes. Now, there's one more thing I want to connect with here. All of our energy equations were originally derived from this work formula, which is transfer of energy to or from the system. So there's one connection I want to make with this formula. This, as a reminder, is an average force. And if the radius is relatively small, say from initial to final, I have my final force here and my initial force up here, my average force would say be somewhere around here. It would be a pretty significant value. So in other words, if the displacement is within this range, in other words, the radiuses are small, then these force values are still pretty large. However, let's say I'm all the way out here, and I go from this initial point to this final point. These values are practically zero, so there is a slight force. So in other words, if I make radius really large, my displacement from one radius to the other will still produce almost no average force at all if I'm far enough away. So to put it very simply, if I'm all the way out here, my force, the force applied, is so close to zero, it might as well be zero. So only distances when the objects are relatively close to each other really matter. If they're very far away from each other, the force is almost zero, so the work done is almost zero. In fact, the force is so small, for all intents and purposes, the force and work done is literally treated as zero. Which brings us to our second point. Field strength versus distance, which is typically written as radius in these equations, is not linear. Most of the change is when the radius is small, and as the radius gets larger, the change gets smaller and smaller and smaller until it's practically nothing. And as a quick flashback to the elastic potential energy video I did, this means we can't simply do change in distance when we're looking for potential energy because our relationship is not linear, just like elastic potential energy. Okay, so 1, gravitational field strength changes over great distances. 2, field strength versus distance is not linear. Now, to bring up my next point, I need to bring back our standard on the surface of Earth gravitational field equation, which actually is linear, because again, the assumption is the gravitational field is not changing. Now, there's something I want to remind everyone of. When we were originally dealing with gravitational potential energy, you can set the reference point for what is 0 joules. In other words, let's say my system is this box and the Earth. If I set my reference point as the ground, then this box has a positive height and therefore positive gravitational potential energy. If I set the table as my reference point, then this box has no height and therefore no gravitational potential energy. However, if I set a point above the box as my reference point, then the box has a negative height and therefore negative gravitational potential energy. In other words, I would have to give my system gravitational potential energy in order to bring this box up to my reference line. Now, with universal gravitational potential energy, this reference line isn't just above your second object.
Your first object is usually a planet.
In this case, we're just going to consider it to be the Earth because that is usually what is used. Your reference line is always above your second object, which in this case is going to be the box. In fact, your reference line way above the object. It is so far away that nothing can be above it. It is farther than the moon, it is farther than other planets, it is farther than other galaxies. It is really, really far away. The actual way it is traditionally stated is that the reference line is at infinity, but the concept of infinity tends to confuse a lot of people. So, how it is typically said in first-year physics courses is that the reference line for universal gravitational potential energy is really, really far away, which brings us to our third point. The universal potential energy reference point, which is 0 joules, is really far away. To coincide with that, that also means that the universal potential energy is always negative, because you can never be above a line that is an infinite distance away. So notice in the example I just did, I do not have the deltas here anymore. I'm solving for gravitational potential energy, not changing gravitational potential energy, which is why I need to set my reference line. So for this form of gravitational potential energy, you can set the reference point, or sometimes it is given to you. For universal gravitational potential energy, the reference point is already stated automatically. It is an infinite distance away. And that never changes. You do not set it, no one else sets it, it is already decided permanently. And keep in mind, going back to my graph here, at an infinite distance, force gravitational is basically 0. So the reasons why we need this relationship: gravitational field strength changes over great distances, field strength versus distance is not linear, the universal potential energy reference point is really, 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 really far away, so your second object is always technically under the reference point, which means universal potential energy is always a negative value. In other words, you would need to gain potential energy in the system to reach that point that is so far away. Now, that being said, change in potential energy can still be positive or negative because it can still be gained or lost. Now, let's do a problem that actually uses this. So, like I said, I'm not going to derive it, but I'm going to show you this relationship. And here it is. Now, let's do a quick comparison to the force gravitational formula. As you can see, they're very similar. There's two differences. One, universal gravitation has a negative symbol because g is a constant, mass can't be negative, and neither can radius. So this forces the negative I was talking about earlier. The second is instead over radius squared is simply over radius. This ensures that my units are newtons times meters, which is joules, where the gravitational equation gives you a unit of just newtons, which is force. I'm going to put this over here. So we're actually going to do a problem here, and I'm going to use Earth as one of my objects, because that is typically the planet you'll be dealing with. And here is our situation. A 120,000 kilogram spaceship moves from a height of 100,000 meters to 180,000 meters. What is the change in potential energy of the ship-Earth system? So I have a spaceship. It is originally at a certain height, called this height initial, and the final point is someplace higher, so that is height final. I will list my givens. Mass of the ship, 120,000 kilograms. My other given is mass of the Earth, which is down here. Now, height is of no use to me. I need radius. And radius has to be from the center of the planet to where the ship is. So radius initial is radius of Earth plus height initial. And radius final is going to be radius of the Earth plus height final. Here's the initial height. I will add this to the radius of Earth, which I have down here, and I will get 6.47 times 10 to the 6 meters. I have height final, which again I'll add to the radius of the Earth, and I get 6.55 times 10 to the 6 meters. Now, one thing to note, this ship is increasing in height. It is getting farther away from the planet. So one thing that is mentally the same as our original form of gravitational potential energy is if the height is increasing, I am gaining gravitational potential energy. And if we are gaining gravitational potential energy, we are definitely expecting a positive answer here. So let's set this up. Change in universal gravitational potential energy would be potential energy final minus potential energy initial, which would be negative g, mass of the Earth, mass of the ship, over radius final, minus negative g, mass of the Earth, times mass of the ship, over radius initial. Now, since I have all these values on the page, and for the sake of space, I'm going to skip showing you all the values, but I am going to show you that they come out to negative 7.307 times 10 to the 12 joules, minus negative 7.398 times 10 to the 12 joules. Now notice since this one has a smaller radius, it also has the larger value, and this double negative ensures that my answer ends up as a positive value, which is what we were expecting. So in other words, the second value is now positive. I do the subtraction, and I get an answer of positive 9.08 times 10 to the 10 joules. This is how much potential energy the ship Earth system would need to gain for the ship to move from the first location to the second. It is moving away from the Earth, so it is fighting Earth's gravitational field. And this energy would need to be provided by the fuel that the ship is carrying, or be transferred from some other type of energy. So a few things to note. If you're going to be assessed on this, it's usually a few different ways. One, you are assessed conceptually on one of these ideas that I brought up in the beginning. Two, you're asked to find what the gravitational potential energy is straight out. Three, you're asked to find change in gravitational potential energy. And four, you may actually be asked to find an energy transfer. In other words, if I did this problem in reverse, and I had an asteroid start from rest and then accelerate toward the planet, where this is my initial point, this is my final, it would lose gravitational potential energy. That gravitational potential energy becomes kinetic energy. And if you find out how much transferred and you're given the mass of the asteroid, you can find out what the velocity is of the asteroid. And if you notice, over these great distances, we're dealing with a lot of potential energy transferring to kinetic if you did that, which is also why the asteroid that hit the Earth 65 million years ago did so much damage. All right, I hope this helped you out. I will end it here. Other than that, have a good day. This is Mr. M signing off.